Hello, my name is Desmond Edagisi, and I'm here to take us on the subject mathematics. We'll be looking at the theme numbers and numeration, and under numbers and numeration, we'll be looking at the topic indices. In our last class, remember we looked at the basic introduction to indices. Well, in this class, we're going to go further and we're going to look at the laws of indices. There are 6 laws in total, but for this class, we're going to look at the first, the second, and the third law. Let's go into our class and quickly see what we have for today. Like we said, we'll be looking at the first 3 laws that govern indices. The first law we'll look at is the product of power law. Next, we'll look at the quotient of power law. And at the end of the day, we'll also look at the power of a power law. But first, there are conditions that govern this law. And one basic condition is that our bases must be same. As we go into our class, we'll understand more. The first law we'll look at is the product of power law. This law basically states that for a quantity A raised to a power m multiplied by the quantity of same base raised to a power n, that would give us our base A raised to the power m plus n. That is, if you have same bases, the powers will add up. Let's prove if this law is true. Suppose we have A raised to power 3. And we were asked to multiply it by A raised to power 2. We'll simply write it out like that. A raised to power 3 times A raised to power 2. We could expand A raised to power 3 as A times A times A, and expand A raised to power 2 as A times A. Then do a simple count. 1, 2, 3, 4, 5. Hence we have 5 A's. And that is our answer. But notice something peculiar. If we added up our powers here 3 and our powers here 2, we could also have A as 5. So it means that the solution we get from going through the long route A raised to power 5 is also the solution we get from taking the short route of adding up our powers as A raised to power 5. This simply proves to us that our law is obviously correct. As we look at more examples, we'll get to understand better. Let's go on. We said earlier that any quantity A raised to a power m multiplied by another quantity A of same base raised to the power n, this would give us our base A and our powers added up together. If we were to use this law for this question, how would we go about this? Now quickly notice our bases. 2 and 2, they are the same. So we are good to go. Quickly we say 2 raised to power minus 2 plus 3. This would give us 2 raised to power 1. Minus 2 plus 3 would give us 1. This is the same as saying 2. Let's take a look again at this example. Remember we said the bases must be the same. So 3 and 3, same base. Now let's go ahead to see what this would give us. We would have 3 raised to the power half plus 3 all over 2. This gives us 3 raised to power 4 over 2. And this gives us, of course, 3 raised to power 2, which, of course, gives us 9. So we see how we apply our first law, the product law. Alright, let's take a look again at this other example. Now we see that there is a difference from what we did earlier. We see here that there is a mixture of numbers and letters in an algebraic mix-up. Say, for example, we were to work this out. We will do this by first collecting like terms. Like terms simply are terms within our expression that are similar in nature. 5 and 4 are similar in nature because they are both numbers. And of course, x and our x raised to power 5 are also similar in nature because they are numbers. So basically, we'll say this as 5 times 4 times x raised to power 5. 5 times 4, of course, gives us 20 times x. Quickly, I like to remind us that whenever we see a quantity, could be a number, could be a letter, on its own, this quantity is same as saying it is raised to power 1. So this quantity is the same as this. Anything raised to the power 1 remains the same way it is. So this, for sake of our work, because some students could make the mistake and just say this is x raised to power 5, but this carries an invisible power. So we'd say this is 1 plus 5 here. And here we have 20x raised to power 6. And that's our answer. Let's take another example here, similar to what we had earlier. In this instance, now we understand, we can quickly work this out as 3 times 2 times x squared times x raised to power 4. This would quickly give us 6 times x raised to power 2 plus 4, which would be 6x raised to power 6. The next law we're going to be looking at is the quotient of power law. This law states that for any quantity a raised to a power m divided by a quantity of same base raised to a power n, that would be our quantity raised to power m minus n. That is, for like bases, our powers would subtract. Let's see if we can prove if this is correct or not. Suppose we were asked to divide a raised to power 7 by a raised to power 3. We would write it out as a raised to power 7 all over a raised to power 3. If we expanded a raised to power 7, we would have this a times a times a in 7 places. If we also expanded our denominator, we would have a times a times a. Let's cancel out like terms. This cancels this out, this cancels this out. And we'll be left with 1, 2, 3, 4. So our answer here becomes a raised to power 4. Quite interesting. But let's see another interesting concept. If we simply took our powers here as 7 and we subtracted 3, which is our other power, we'll also come up with 4. So a raised to power 7 divided by a raised to power 3 will simply become a raised to power 4, which is of course the same value we have here. So this simply tells us that instead of going through this long route, we could simply subtract our bases when we have our operator as a divider. Therefore, we can say here that our law once again is correct. If we had c raised to power 7 and we were asked to divide it by c, we said in the last example that any quantity left by itself is actually raised to power 1. This is same as this. For the purpose of indices, students need to get this basic understanding, or we may make mistakes. So how would we solve this, knowing what we know now? This would be c raised to power 7, using our laws, minus 1, because this c left of itself is actually c raised to power 1. Do we get it? So how would we work this out? This would be c raised to power 6. Very simple. Now let's take another example. If you were asked to simplify x raised to power 3 divided by x raised to power minus 5. Knowing our rule, how did we solve this? We will say x raised to power 3 minus 5. This minus 5, remember, it's on its own, while our operator here is minus. And of course, we know that minus times minus would give us a plus. So this could be written as 3 plus 5, which is equal to x raised to power 8. We get it, don't we? Alright, let's move on. Let's look at another example again. This brings us to a very important concept. Whenever you have an expression given to you in a bracket, your bracket acts to separate certain situations from one another. For example, our 5 is outside of this bracket. It tells us that whatever is going on in the bracket, it's in a different environment. But of course, later on, we can come to multiply 5 by everything that is within the bracket. So, there is a separation. Now, if you were asked to solve this, knowing what we know, how would you go about that? First, we will work out the expression within the bracket first. And that would be, let's leave 5 outside of our bracket. Y raised to power 9 minus 5. That again would be y raised to power 4. Now we can multiply our 5 with whatever is in the bracket. And that gives us 5y raised to power 4. That's our answer. Let's take a look at this other example. 22n raised to power 7 divided by 2n raised to power 3. Like we said earlier, let's take the like terms. We have a combination of both numbers and letters. We would write this as 22 all over 2. Then we would have, taking like terms, remember we said n raised to power 7 all over n raised to power 3. Here would have it 1, and it will go in here 11 times. So this would give us 11, and our n raised to power 7 divided by n raised to power 3. By our law, this would be minus 3, which would of course give us 11n raised to power 4. Do we understand? Is that clear enough? Alright. The next law we're going to be looking at is the power of a power law. This law states that for any quantity A raised to a power m, all enclosed raised again to a power m, for such a case, it states that our quantity becomes A raised to power m times n, which of course gives us mn. So, when you have a power raised again to another power, simply multiply our powers to give mn. Let's try and prove if this law is correct or not. If you were given a raised to power 4 and you were asked to raise it to a power 3, we'll write it out like this. A raised to power 4 raised to power 3. We would write this out as a raised to power 4, of course, in 3 places, which is a raised to power 4 times a raised to power 4 times a raised to power 4. If we were to further expand this, we'd have a long string. That is a times 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 a. That's pretty long. But a shortcut would be using the first rule of indices that we learned earlier, which would be a raised to power 4 plus 4 plus 4, which of course would give us a raised to power 12. This is good enough, but there is another shorter method. Let's see. If we took our powers 4 and we multiplied it by the other power 3, would also come up as 12. So this expression becomes a raised to power 12. So if you notice, the route we took to get a raised to power 12 gives us the same answer if we took this shorter route of multiplying our powers directly. 4 times 3 gives us 12. So we can say that our rule, which states that our powers multiply each other out, is also very correct. As we look at some examples, you will get to understand better. A little better. If we're given this expression 2x raised to power 3, all enclosed in brackets raised to power 4, how would we go about this? Remember we said something about the brackets? The bracket encloses everything within it and lets us know that whatever operator that is outside of it works on everything that is within the bracket. One mistake students may make here would be to assume, because now we've learnt about the law that our powers multiply, they would probably say this is 2x raised to power 3 times 4, and they would say this is 2x raised to power 12. This is wrong. This is incorrect, because we said that our bracket tells us that our operator outside works on everything in between. So let's solve this again. This would be 2 raised to power 4. This our 2 here is also affected by the power. Okay, multiplied by x raised to power 3 times 4. So this would give us 2 times 2 times 2 times 2. This would be 16 times x raised to power 12. So our answer would be 16x raised to power 12. Let's take another look at this example. There's a point also that we must understand in this kind of situations. For every negative quantity a raised to a power that is odd in number, of course we know what odd numbers are. Let's say for example 3. Our final answer would end up being negative. But for every quantity, negative quantity a raised to an even number, our final answer would always turn out positive. Let's solve a quick one. Let's say we have minus 2 raised to power 3. 3 is an odd number, and our number here is negative. If we were to work this out, let's expand it. We would have something like minus 2 times minus 2 times minus 2. this would give us minus 8, because our minus cancels out, but 1 is left. If we had it, on the other hand, raised to an even number, this would be minus 2 times minus 2 times minus 2 times minus 2. 2 times 2, 4 times 2, 8 times 2, 16. And our negatives cancel out, so we have a positive answer. In general, repeating what we said earlier, for whenever we have a negative number raised to an odd power, you end up with a negative answer. But if we have a negative number raised to an even number, you always end up with an even number. I hope we'll remember that as we go on. Alright, let's quickly solve this. Remember we said for all content within a bracket, whatever operator we have outside of it affects everything. So ensure when you are working out your solutions that every object is picked. So we have minus 3 squared times d raised to power 3 times 2. This would give us 9 times d raised to power 6, and this would give us 9d6. Once again, remember we said if our power here was an odd number, our answer would have ended up being negative. But because our power was even, our answer was positive. Alright, let's move on. If we were given such situations to solve, how would we go about this? Again, see our power is odd and we have a negative number. Can you predict what our answer would be in this case? It would be negative. Let's go on and see. This would be minus 4 raised to power 3 times g raised to power 5 times 3, which is equal to minus 4 cubed would give us, first, it's a negative answer. 4 times 4 is 16. 16 times 4 is what? 64. G raised to power 15. And that's our answer. So we see, because it was raised to an odd number, our negative number ended up giving us a negative answer. Alright, let's quickly look at this. Again, remember we said any number left of itself is actually raised to a power 1. So for this situation, we would have what? A raised to power 3 times 4 times b raised to power 1 times 4. So this would give us what? A raised to power 12, b raised to power 4. That's our answer. In summary, we've looked at the first 3 rules of indices. We've looked at the product of power law, which tells us that a quantity a raised to power m times a quantity of like base raised to power n is equal to our quantity a raised to power m plus n. Means that for like bases, our powers add up themselves. Next, we look at our quotient of power law, which states that a quantity a raised to power m divided by a quantity of same base raised to power n would give us our quantity a raised to power m minus n. Meaning that for like bases that divide one another, our powers will be subtracted from themselves. And finally, we looked at the power of a power law, which tells us that a quantity raised to a certain power, if it is raised again to another power, we simply multiply out our powers. And hence, for this instance, if we have a raised to power m raised to power n, we'll simply multiply our powers to get a raised to power mn. Once again, we've come to the end of this class. But guess what? In the next class, we're going to be looking at the 3 remaining laws. It promises to be very exciting. And I hope to see you in our next class. For me, it's bye for now.